Welcome back to CS111. In the previous lecture, we took a look at some relatively straightforward algorithms for sorting. In this lecture, we're going to take a look at some more advanced approaches. These ones are more complex to go and implement and also a little bit more challenging to understand, but they give us a bit of a benefit in terms of improved performance in many circumstances. Let's start off by taking a look at Shellsort. In our previous lecture, we looked at Insertion Sort, which is a fairly straightforward way of going and organizing the data in an array or other data structure. One of the big shortcomings of Insertion Sort is that it can require a lot of moves as it goes and organizes our data. We have to go through, identify the correct location where our new item is going to be inserted, and then we've got to make room for it by going and moving all of the other items that are to the right of there over by an element. Pretty early on, computer scientists started looking for ways that they could go and sort data that would be a little bit more efficient. Donald Shell developed what is now known as Shellsort in 1959. The idea here with Shellsort is that we're going to go and use multiple passes with smaller moves to go and organize things. With Shellsort, rather than going and trying to sort an entire array at one time, we go and divide it up into a series of subarrays that we go and sort. We don't go through and partition the array like to a first half and a second half. With Shellsort, we go through and take every H element. So if I'm going to go through and use a size of, for example, H equals 5, what I'm going to do is I will go through and take elements 0, 5, and 10 and sort those. And I'll have a whole series of those sorts. So then I'll have 1, 6, and 11. 2, 7, and 12. 3, 8, and 13. And 4, 9, and 14 if I'm going through and sorting an array that has 15 elements. I go and sort within those particular sets there. And when it's done, I'm going to go through and end up with an array that is partially sorted, basically into, in this case, 5 groups, since I'm using the size of H of 5. Now, this is obviously not a fully sorted array by the time we get down to the end, after we go and complete all of our sorting on the size of H equals 5. But what we can then do is take that partially sorted array and go through and shrink the size of H and sort again. And we'll keep on shrinking the size of H until we get to where H is equaling 1, which means that we're sorting every single element. And when we sort there, we're going to have a final sorted data set. Let's go ahead and work this example through until it's fully sorted. So here we have the output of where we sorted with H equals 5. So essentially we have 5 sorted sets inside of this array. We'll go and do a pass with a smaller size of H. We'll do H equals 3 here. So we're going to go and sort every third element. So now in yellow, we have 3 groups that are sorted. So you can see if we start off here, we have with the first group, we have 30, 37, 44, 55, 85. And then we have 10, 16, 57, 67, 74. And our last group is 26, 48, 68, 79, and 97. So you can see that we're slowly getting things closer to being sorted. We'll go and do a pass here with H equals 2. So we're going to sort every other item. So if we go down here, if we take a look, every other item is going to be in sorted order. And then finally, we have to go and sort with h equals 1. That's going to be the endpoint for our sorting in every case where we go and use shell sort, because that's what's actually going to get us to a fully sorted array. And once we go and sort every item, we're down to where we have things fully in ascending order. But kind of the advantage that you see with shell sort here is that rather than maybe having to take something from the very end, if moving it way up towards the front, like if we were doing insertion sort, we're going to just do smaller moves as we go and get stuff incrementally closer to where it needs to be. So, by the time we get to here with our output of h equals 2, we're pretty close here. Some of these things are already in sorted order, or some of the ones that aren't, maybe we have to go through and just move one position here. Like we need to swap 10 and 16. When we're working with shell sort, we need to make sure that for our very last pass, we have a gap size or value of h of 1 in order to fully sort our data. We need to make sure that we're not skipping over any elements. We've got to sort every single one on that last pass. For the previous passes, though, we want to go and figure out an appropriate value of h to use. We don't want to start off with h equaling 1, because if we did that, then our shell sort would really just degenerate to insertion sort. As it turns out, the values of h that we use can have a very significant impact on how shell sort performs. This has actually been an area of quite a bit of research in terms of finding out what sizes of h are going to work best. There have been a number of different strategies that have been researched going back to right after shell sort came out in 1959. And this is an area that still continues to get occasionally new papers published in. One fairly common approach is one that was proposed by Donald Knuth in 1973. His approach provides gap sizes or values of h that will allow shell sort to run in a worst case of big O of n to the 3/2 or 1.5 power. The way Knuth's sequence works is it assumes that for our last pass that we're going to have an h value of 1. For any earlier pass, k, and k is something that's actually going to go through and count down. So our final pass is going to have a k for the number of the pass being 1. We're going to go through and calculate the gap size to use with the formula 3 to the k power minus 1, and then we're going to divide all that by 2. But there's a caveat with that. We want to make sure that we don't end up with a gap size that is larger than essentially 1/3 the size of our array. Can't be bigger than the ceiling of the number of elements we have divided by 3. If we were just go through and take those rules, the last couple numbers in sequence for our h values would end in 121, 40, 13, 4, and 1. If we were to go and apply these rules to the 15 element array that we've been working with here, we would end up with gap sizes for our passes of 5, 4, and 1. So we would have 3 passes altogether. Let's go ahead into Eclipse and see how we can go and implement shell sort using Knuth's formula for determining our gap sizes. Let's take a look here at how we can implement shell sort. We're going to do this as a static method inside of the Shellsort class that's part of the starter code for this lecture. So in this class we have a main method that's already there that goes and generates an array of 20 integers, and then it will go and print them out. We've got a spot here for where we can go and call the sort method we're going to write, and then it'll go and print out the values after things have been sorted. For our method here, we want it to be public, and we're going to make this method be static so that we don't have to instantiate an instance of the Shellsort class in order to go and use it. We're going to have to take a generic type for the array that we're trying to sort, and we do need to go and place some restrictions on the types that we can allow for this array to make sure that they go and implement the comparable interface. So for this, I'm going to go and specify a generic that t extends comparable, and then comparable itself has a generic parameter, and I'm going to say question mark super t, and that basically means that it's going to have to be t or a superclass of t here. Once I specify the generic, I want to list my return type, and that's going to be void because we're going to actually go and just sort the array as it exists. We're not going to go through and return a new array. For the name of the method here, we're going to do an iterative sort, so I'm going to go and put that in the name here. So this is going to be iterative array shell sort. And we're going to go and provide our parameter, which is going to be a t array that we'll call sort array. Inside the method, the first thing that we're going to have to do is determine the number of passes that are required. And we're going to go through and actually use a while loop to help us go and figure this out. We're going to assume that we need at least one pass here to go and feed into the formula. This is actually just really going to kind of save us from one fewer loop iteration, and it also is going to go through and help us correct for an overcount problem later on. So you might figure that we'll assume 0 in case we had 0 potential items in the array, but we're not actually going to go through and save ourselves any benefit there. We're going to use 1 for this value. For the while loop, what we're going to do is we're going to use Knuth's formula to go through and figure out what the gap size or the h size should be for a particular number of passes that we've had. And we're going to go through and find the largest gap or h size that is going to be smaller than our array. So this formula's got a couple parts to it here. We're going to go and start off by going through and raising 3 to the exponent passes. So for that, I'm going to do math.pow, and the first argument is going to be the number 3. The second argument is going to be my passes variable. So that's going to be the power that we're going to go and raise 3 to. I want to take the result from that, and I'm going to subtract 1. And then I'm going to take that result, and I'm going to go and divide it by 2. So I'm going to go ahead and wrap that whole thing inside a set of parentheses. So I want to make sure that that is less than sort array dot length. And I need to put that inside of parentheses. So we're a couple layers deep there. But what's going to happen here is that while that's true, we're going to go through and increment the number of passes required. So I'm just going to take that passes variable and I'm going to increment it. Now, one sort of odd thing that's going to happen here with this loop is that it's actually going to overcount by 1 the number of passes that we want. And the reason why is going to be that if I can go through and successfully solve this formula here, I can go and say that I'm going to increment passes. But what's going to happen on that very last time I was able to fit, when I come back with that increased number of passes, I'm no longer going to be smaller than the sort array length, so then I'm going to go and fall out of this loop. Basically, the net result here is that when I go and use that passes variable, I want to go and subtract 1 from it to go and correct for that overcount situation. Since I'm going through and starting this off with 1, if I have a case where I'm not actually sorting anything because there is nothing in the array, I'm going to go through and loop for 1 minus 1 equals 0 passes. So it still all works out in the end. It's just, the variable, we're going to have to do a little bit of manipulation throughout. Using that passes variable, we're going to go and start our loop to perform the shell sort. And we're going to make sure that we go and adjust for the pass overcount from the final loop. So I'm going to do a for loop here. I have a fixed number of iterations this is going to run. I'm going to go and create this variable that I'm going to call pass to keep track of what pass I'm on. And I'm going to initialize it to passes minus 1. So I said I want to go and subtract 1 from passes. That's where I'm doing it. We're going to go and loop while pass is greater than or equal to 1. and each time through we're going to go and decrement pass. Inside this loop, I'm going to start off by going and calculating the gap size, or the h size, for this pass. For this here, I'm going to go and use Knuth's formula from up above. So I'm going to go and take math.pow, and I'm going to go have 3 as the base and pass as the exponent. I'll subtract 1 from that, and then I'm going to go and divide it by 2. But there's another case I have to go through and take care of here. So from Knuth's, it said that the gap size should be the smaller of this or the ceiling of the size of our array divided by 3. So I need to go through and take care of that second situation, the ceiling of the size of our array divided by 3. So what I'm going to do here is to find the smaller of the two. I'm going to go and use the math.min method. So this is going to go through and return the smaller of the two arguments. So my first argument is going to be from Knuth's formula there. And the second one is going to be actually part of Knuth's formula too, but the other part. We're going to go through and find the ceiling. So it's going to be math.ceil for sort array.length, which is the size of our array, divided by 3.0. And I'm specifically doing 3.0 so that I get any decimal part there because I want to take the ceiling. If I did just divide by 3 without the 0.0, that would do integer division and I would get the floor, which is not what I want. I want to be able to take the ceiling, so I've got to divide by 3.0. So I'm going to use the result of this formula for my gap size, however many eighth-inch elements I'm trying to go and get. Because I'm dealing with elements which are integer index based, I'm going to go and cast this here to be an int. And I'm actually going to store it in an int type variable that I'm going to call gap. Once I have that gap calculated, I can go through and basically start doing what is the insertion sort algorithm off of that current gap size. So I'll do a for loop here. I'm going to say int offset is 0, and while my offset is less than the gap, then we're going to go through and increment offset. So offset's essentially going to be which of the h different starting positions I'm going to go and use. And inside of there, I'm going to have another loop. So this one is going to go and loop through the elements in our current pass. And this one here, we'll do a for loop. We're going to say our current index equals our offset plus the gap that we've got. The reason why we're doing offset plus gap here is that current index will actually point to the second element that we're going to look at, because later on we're going to go through and compare this one to the first element, and I'll go and subtract gap back off when I go and calculate that index. So we're doing plus gap here, and we're going to go through and loop while current index is less than sort array.length, so I don't overrun the end of my array. Each time through, we're going to go and add gap to current index because I need to be able to skip over elements in between. So I've got current index plus equals gap. The first thing that we're going to do inside this loop is we're going to go and calculate the index of the item immediately before current index, assuming that we're minding our gaps here. So I'm going to create this int here that I'm going to call prev index, and I'm going to set it equal to the current index minus the gap. So initially what we'll run into is that prev index will be the first instance of our the values that we're going to be sorting with this particular gap size, and current index will be the second item that we're going to be sorting. Current index is going to go and march on down with each loop iteration here because we're doing plus equals gap. Prev index will also march on down. So prev index is always going to be the one that is immediately before current index. Next, we're going to go and get the value that we are trying to insert, and we're going to stick it in a temporary variable. That way, when we go and do the insertion sort, we're going to have to shift stuff around, and this way we can go and overwrite that value and not have to worry about losing it. So I'm going to create this var here that I'm going to call insert value, and I'm going to set it equal to sort array sub current index. Then we're going to have to go and loop until we find the right spot to go and insert things. And we're going to be shuffling stuff around as we do that. So I'm going to have a while loop here, and there's going to be two conditions to it. The first one is that prev index is going to have to be greater than or equal to 0 because I can't move backwards before the start of my array. The second condition is going to be the result of going and comparing the value that I'm trying to insert with what's in prev index. And I'm trying to code my approach here in a way that will work with nulls so that I don't get null pointer exceptions. So I'm going to use the objects.compare method with a null-friendly comparator. So for this here, my second condition is going to be java.util.objects.compare, and I'm going to compare insert value to sort array sub prev index, and then my third argument is going to have to be my comparator. And here I'll do java.util.comparator.nulls first. So if there is a null value, it's going to get sorted so that's before anything else. Inside of the parentheses for nulls first, I'm going to have to say what to use for comparing things when it's not a null. And I'm going to use the natural order comparator, which will fall back onto the compare to method of the object that we're dealing with here. So this is going to be java.util.comparator.natural order. Closing natural order, I'm closing nulls first, and I'm closing compare to there. So after 3 closing parentheses, I'm going to say that if that is less than 0, and I'll have 2 more closing parentheses afterwards, I'm going to do what's inside the body of the while loop. And what I'm going to do here is I'm going to have to go through and check another position further over to the left. So what I'm going to do is take what's in the current prev index, and I'm going to go and move it to the right, because I'm going to have to keep on doing that to go and free up space. So we're going to go and move existing value to the right 1 position. And I'm going to say here sort array sub prev index plus gap. I'm going through and keeping track of that gap since I have to skip elements in between. And I'm going to set equal to sort array sub prev index. Then I'm going to go and update prev index to be 1 position further to the left. So prev index is going to be prev index minus gap, or I could have also done this prev index minus equal gap, but sometimes I find this to be a little bit more obvious way of going and showing what I'm doing rather than doing minus equal, especially where the minus might be easily overlooked. Once we fall out of this while loop, we found the correct spot to go and insert our new value. So we'll go ahead and do that. So we're going to store value in correct location. We're going to say sort array sub prev index plus gap is equal to insert value. And the reason why I'm doing this prev index plus gap here is the fact that we're going through on this last pass, we subtracted gap. And for example, that might have put me at a negative index. So I need to go and correct for that to move back. So that's why I'm doing plus gap here. At this point, we have our Shellsort method coded up. Let's go ahead and give it some Javadoc. And let's go up to our main method and call our Shellsort from in there where it indicates to do that. So I've got this comment here. It says call sort method here. I'm going to call Shellsort dot iterative array Shellsort, and I'm going to go and pass it numbers since that's the name of our array. And we'll go ahead and run this. And so you can see we've got these unsorted values before, and afterwards everything comes out nicely sorted. Shellsort is pretty rarely done recursively. Normally, if you're going to use Shellsort, you're going to use an iterative implementation similar to what we did. Frankly, the iterative implementation is complex enough. Going through and making it recursive doesn't really simplify things any. It just makes stuff more difficult to understand. So really, Shellsort, you're normally going to see people just stick with an iterative implementation. Shellsort's performance is heavily affected by the values of H, the gap sizes that you use. That have a big impact on how many passes you have to go through and make. In general, the worst case scenario that you're looking at is big O of n squared time. The average case and best case are going to be on the order of big O of n log n. So not too bad as far as things go here. Taking a look at some of the pros and cons of Shellsort, overall it has pretty decent performance as long as you go through and choose appropriate values of H, and Knuth is a decent improvement over the original version of Shellsort. There are other variations since then, because Knuth is from 1970s, that have gone through and improved things even more. Shellsort is nice because it's an in-place sort. Other than that temporary variable, as we go and shuffle stuff around, it really doesn't have any additional memory requirements. So this can be helpful when you're going and working with large data sets that they don't really impose a huge burden on how much RAM you need to have available. In terms of cons, Shellsort's pretty complicated. It's hard to understand, and it's also hard to go and code, especially with all those nested loops. The next algorithm that we're going to look at is merge sort. Merge sort takes a divide and conquer approach to things, as you can see with the animation that's shown on screen. What it does is it recursively goes and divides the array that we're trying to sort in half. And note I said recursively. This is an algorithm that is normally going to be implemented using recursive methods, not iteratively. So we started off in this animation with 8 elements in one array. It divided that in half, so we got 2 4-element arrays. It divided that in half again, so we ended up with 4 2-element arrays. And then it divided each of those into single element arrays, so we ended up with 8 single element arrays. Basically, our base case is when we get down to there being a single element. And when we get to that point, we're going to start returning back up our chain of recursive calls. When we return back up the chain, we're going to go and sort each of those subgroups that we're combining at that point. So we'll go through and take the 2 single elements that we're combining into a group of 2, and we're going to end up doing it so that that group of 2 is sorted. And then when we combine 2 groups of 2, we're going to go through and do that so that our resulting group of 4 is fully sorted. So we're basically sorting all these smaller pieces and then going and combining them. As we return from our different recursive calls, we're going to go and combine our 2 sorted subunits into a larger sorted subunit. And we just go and work our way through our chain of recursive calls like this. Eventually, when we get to the bottom of the call stack, we're going to end up going and combining our 2 sorted halves, and then we'll end up with a sorted whole. Let's go ahead into Eclipse and see how we can code up merge sort. Merge sort is normally implemented recursively, and it involves 2 methods. One of them is the recursive sort method, and that's what goes and divides our data set in half for each recursive call. The other method is normally called merge, and what it does is it goes and combines those smaller groupings into larger ones by going and merging the values in a sorted order. Let's go ahead and start off by coding that merge method first. This is actually the part where most of the guts of this algorithm is located. This is going to be something that we just want to use internally here. So we're going to go and designate it as a protected access modifier. And it's going to be a static method here. And we need to go and provide our generic parameter. So we want t, but we want to make sure that t is something that goes and implements comparable. So we'll say t extends comparable. And then for comparables generic, we want the wildcard for the question mark super t to designate that it has to be t or a parent of t. This is going to be a void return type here, and we'll call this method merge. It's going to take 4 parameters. The first one's going to be the array that we're trying to go and sort. So that'll be an array of type t. We're going to have then 3 indexes. We'll have an int that we're going to call left index. That's going to be the leftmost index we're going to sort. We're going to have another int that's called middle index, and that's going to be basically the midpoint of where we're going to divide those 2 halves up. And then we'll have another one that we're going to call right index, and that's going to be the rightmost index that we're sorting. And we're defining these indexes as including these points. So up to and including right index will be sorted here. This implementation is designed, as we're coding it right now, to go and work with an array. Although you could go through and adapt it if you want to work it with nodes instead. Inside the method, we're going to start off by going through and creating subarrays for each half. So I'm going to create a left half that's going to be an array of type t. And to go and make it, I'm going to use the copy of range static method from java.util.arrays. So I'm going to say java.util.arrays.copy of range. And what copy of range does is it will go through and copy an array from a start index to an end index that I go and specify. So I'm going to go and take sort array as my array. My start index for the left index here is going to be determined by the left index that is passed in. My right index is going to come from middle index plus 1. The reason why I'm using middle index is because this is the left half. I want to take the left to the middle point. I'm doing the plus 1 because I need to go through and make sure that middle index itself is actually included in the copy. And copy of range, like a lot of things in Java, it includes left index, but it excludes the end point here. So I'm doing the plus 1 to make sure that I actually get that one pulled in. I'm going to do a mirror of my left half copy for the right half. Here I'm going to say right half is equal to java.util.arrays.copy of range. For sort array, I'm going to go through and start at middle index plus 1 because I want to make sure that middle index only appears in one half, and since I've assigned it essentially to the left half by doing middle index plus 1, I want to make sure it's not here in my right half. And for the last argument, that's going to be right index plus 1 to account for this being excluded from the copy. So we need to make sure right index is there, so we'll do right index plus 1. Once we've gone and made our copies of the subarrays, we need to go through and declare some variables to track our current position in each array. These will all be ints, and I'm going to say that I'll have left half index I'm going to initialize to 0. I'll have right half index that's also going to be initialized to 0. And then I'm going to have merged index, and this one is going to keep track of where I'm at in sort array, where I'm actually going and putting the values back in after we have sorted things. And I'm going to initialize that to left index because that's going to be the left position of where our new sorted section is going to start. With those variables set up, we're going to go through and start to merge the left and right subarrays. We're going to use a while loop for this, and our while loop is going to have two conditions. We're going to say that left half index has to be less than left half dot length, and right half index has to be less than right half dot length. What this does for us is that basically it makes sure that we're not going to overrun the bounds of either half array. It's going to make sure that really what's happening here, that there are still an item in the left half that I can go and compare against an item in the right half. And when I do that comparison, that's going to tell me which one of those should go first in our merged array. Our comparison is going to be something that will be null safe. So it's going to be kind of a long statement here, but we're going to go through and use that java.util.objects.compare method to do this here. And obviously this needs to be inside of an if statement. I'm going to go and compare left half at left half index against right half at right half index. And so that I can work with any nulls that might be there, I'm going to go and pass a comparator that is null safe. So I'm going to use java.util.comparator.nulls first to go ahead and place nulls first. And then inside the parentheses, as an argument to nulls first, I'm going to tell it that I want to use the natural order comparator if I have a value that is not null. So we'll do java.util.comparator.natural order. And I need to go and look at the return value from compare, which is going to be an int. And I'm going to check to see if it's less than 0, which essentially means that the left half is smaller than the right half. If this is the case, we're going to go and copy the value from our left half into our merged array. So we're going to say sort array submerged index equals left half sub left half index. And then I'm going to go and increment left half index to keep track of our position in that subarray. The else clause is going to take care of where the right half is smaller or they are equal. For this, I'm going to say sort array submerged index equals right half sub right half index, and we'll go and increment right half index. And then after that if else block, we're going to have to go and make sure that we increment our position in the merged array. So we'll do merged index plus plus. So this while loop will take care of the case where we have a value in the left half that we can compare against a value in the right half, and it's going to put the smaller one first. We're going to fall out of that while loop when we don't have pairs of items to go and compare anymore. It could be because there was an uneven number of items in the two half arrays. You know, if I have 7 items in my parent array, I can't divide that into an even number. So one of them is going to have 3, one of them is going to have 4. So I might end up with an unbalanced condition there. I could also run into a case where, for example, I had a bunch of small values in left array, and I ran out of things in left array, but there's still stuff left in right array. I need to go and take care of any of these situations that might occur where there are still items remaining in left array or right array. There should not be things in both. It should only be one or the other. What I'm going to do is I'll create a pair of while loops to go and empty out those subarrays and just copy things back into the merged array. They'll both be there, but only one of them should actually end up running depending on how things shake out. When I fall out of this while loop, that basically means that I am out of matched pairs of values that I can go and combine. I've either run out of things from the left half or from the right half. There might still be items left in the opposite half, though, of whichever one ran out of things. So I might have exhausted all the items from my left half, maybe because they were smaller numbers. But I might, for example, still have a couple things left in my right half. I need to make sure that those values go and make their way back into my merged array. So what I'm going to do here is have two while loops that are just going to go through and iterate over left half and right half respectively to go and finish copying over anything else that's left. And we'll just do left first here, but it really should not matter. Only one of these while loops is actually going to run. So I'm going to say while left half index is less than left half dot length. I'm going to go and copy the value itself. So we'll do sort array submerged index equals left half sub left half index. And then I'm just going to go and increment my counters. So we'll say left half index plus plus and merged index plus plus. We'll have mirror image of that to go through and copy anything remaining from the right subarray. So while right half index is less than right half dot length, we're going to go through and copy our value. So we'll do sort array submerged index equals right half sub right half index, and then we'll go and increment our counters. So this one here will be right half index plus plus and merged index plus plus. And that goes and finishes up what we need to have for this method, aside from some Javadoc. In my comments, I just went and noted that for the values here where I'm specifying indexes, that the index is included in the range that I'm going to be dealing with. That way, there's no confusion about if it's inclusive or exclusive, because I've explicitly gone and said in the Javadoc that it is inclusive of it. I'm going to do the left array first. So we'll copy anything remaining from left subarray. And here we'll do a while loop. We'll say while left half index is less than left half dot length. We'll go and copy our value. So we'll say sort array submerged index is equal to left half sub left half index, and then we'll go and increment both of our counters. So we'll do left half index plus plus and merged index plus plus, and then I'm going to have basically the mirror image of that for clearing out the right subarray. So we'll say while right half index is less than right half dot length, we'll go and copy our value. So we'll have sort array submerged index equals right half sub right half index, and then we'll increment these counters. So we'll have right half index plus plus and merged index plus plus. And that basically takes care of the merging process. Let's go ahead and put some Javadoc on our method here so that we can show what all is going on. And note that I made it really clear with these indexes that they are inclusive here, so that I don't have to go through and do the +1 that I did with like copy of range when I go and provide values. Now that we have that helper method out of the way, let's go and create our actual recursive method. Now I'm going to make this be protected because I'm going to create a public method that's going to be a little bit friendlier for people to go and use. That will go and kick off the recursive process. In addition to being protected, this is going to be a static method, and we have our same generic values that we've been using for all the other cases. So t extends comparable, and then the generic for that is $super t. This is going to be a void return type, and I'm going to call it recursive merge sort. It'll take 3 parameters. The first is going to be an array of type t that we'll call sort array. The next is going to be an int that we'll call left index. That's going to be the left index of where we're actually going to be sorting. And then we'll also have an int called right index. The body of this method is actually pretty simple. The first thing that we want to do is make sure that we don't have the base case. Our base case here is going to be where we just have one element being sorted. So if the left index is greater than or equal to the right index, we're just going to return. And that's where we're going to start actually combining things as we go back up the chain here, instead of dividing them up into smaller groups. If we do need to place more recursive calls, what we're going to have to do first of all is figure out where the middle of our array is going to be. So I'm going to say var middle index is equal to left index plus, and then inside parentheses we're going to have right index minus left index, and we're going to divide that by 2. So what we're doing here is figuring out of the part that we're actually trying to sort right now, essentially where the middle is of that, and we're doing an integer division here so we don't get decimal points back. And then we're going and adding that onto left index so that we can kind of figure out inside the part that we were actually trying to sort, where is the middle of that. Once we have our middle index calculated, we can go and place a pair of recursive calls. So we're going to have a recursive call to go and sort each half. So we'll have, for our first one here, we're going to call in the merge sort class the recursive merge sort method. I'm going to go and pass sort array, left index, and middle index. And then we'll have another recursive call where we're going to pass sort index, middle index plus 1, and then right index. So we're going to go and sort the left half with this first call and the right half with the second call. After that, we're going to go and call merge to stitch things back together. So merge sort dot merge, and we're going to pass it sort array, our left index, our middle index, and the right index. So when we go and use this with actual data here, we're going to keep on going and placing these recursive calls as long as we can divide things in half. Eventually, when we get down to one element, we're going to start returning, and then as we start to return, we're going to go and take each half that we got from our recursive child and go and stitch that together and then return it back up the chain. Let's go and provide some Javadoc here. So this is going to perform merge sort on an array. T is the type of data being sorted. Sort array is the data to be sorted. Left index is the leftmost index to sort, and I'm going to note that it is inclusive of that. And then right index is the rightmost index to sort, and that's also inclusive. Let's go ahead and create a public method to go and kickstart our recursive calls. That way, all we have to do is just go and provide the array that we're trying to sort. We don't have to worry about providing left index and right index. So this is going to be a public method. It'll be static, and we're going to have our same T generic stuff. T extends comparable, question mark, super T. This is going to be void, and I'm also going to go and call this recursive merge sort. And the difference here is going to be we'll have just one parameter, and that's going to be an array of type T that we'll call sort array. Inside the body, we just need one line of code, and that's going to be to go and call our recursive method to get things started. So I'm going to say merge sort dot recursive merge sort, and our first parameter is going to be sort array, since that's the array we're trying to sort. Second one's going to be our left index, which is 0, and the third one's going to be the right index. And what we want to do here is take sort array dot length, and we're going to go and subtract 1 to account for the fact that we're using 0-based indexing. I'm going to go ahead and copy the Javadoc for our protected version of recursive merge sort up to the public one, and then I'm just going to go and get rid of the 2 params for left index and right index since those don't apply. Now that we have merge sort coded up here, let's go and use it. In the main method, where we have things indicated, let's go and call recursive merge sort. So I'm going to say merge sort dot recursive merge sort, and I'm going to use the public version here that just takes one parameter, and I'm going to go and pass it the array numbers. We can go and run this, and you can see the values we had before, and then after the sorting here, everything's nicely in order. Because of how merge sort works with breaking things down into one element groups and then rebuilding, there actually really isn't any difference in its time complexity depending on whether things are sorted or not sorted or sorted in reverse order. Everything is big O of n log n. Compared to some other algorithms, in terms of pros and cons, merge sort has pretty decent performance, and overall it's fairly easy to understand, which is a nice thing to have in an algorithm. It works well with node-based linked lists too, so that's also a nice thing. It does have some significant cons though. It's not necessarily the fastest. There are some other algorithms that have better best case performance. And the process for going through and merging things is a little bit complicated. Perhaps the biggest knock on merge sort is that its normal implementation, like what we've looked at here, is not in place. It goes and creates copies of the arrays that we're trying to go through and sort. So it does have higher memory requirements, and if you're trying to sort a really large array, it's potential that could become a problem. Maybe you just don't have that amount of memory readily available. The final algorithm that we're going to look at is quicksort. And this one is also a divide and conquer recursive style approach. This is not something that you'll normally will see done iteratively. What quicksort does is it goes and just selects an arbitrary element. Doesn't really matter which one, but it's going to go and call that a pivot point. What it's going to do is it's going to take the value there from that pivot point, and it's going to go and create two subarrays. It's going to go and have a partition that will be values that are smaller than the pivot point. Those are going to be to the left of the pivot, and then ones that are larger to the right of the pivot. So in this animation here, the shaded area is the part that we're going through and focusing on sorting. The red bar is the pivot point for the current pass, and then you can see it's going through and swapping around values depending on where they are relative to that pivot point's value. Let's take a look at an actual step-by-step example that we can work through. Let's say that we have this 7-element array that we're trying to sort using quicksort. We're just going to go and pick a pivot point, and I'm arbitrarily going to choose to use the last element for the pivot for each of these. I can do whatever I want to be the pivot point. I could be the first, I could be the last, it could be the middle, it could be some random value. Doesn't really matter for the operation of this algorithm. I just have to pick something. So the value that's in my pivot here is 50. So what I'm going to do is I'm going to construct partitions of values that are less than and greater than my pivot. So you can see I went and took that 50 and I went and made a partition of things that are smaller than it. So I've got 30, 46, and 40 from that. And then I've got ones that are larger. I've got 51, 88, and 95. I just started from the beginning of my array and worked way through. Right now, at least the left one here is not in sorted order. The right happens to just be in sorted order because of the values that I had originally, but that's just coincidental. Now what I'm going to do is I'm going to work through these new groups and pick a new pivot point. So for this left partition, my pivot's going to be 40. And then I'm going to repeat that process. So I'll have now 30, and then I've got my pivot point of 40, and then I've got 46 is larger than that. We'll do the same thing on our right partition. So I'm going to pick 95 as the pivot point. I'll have a group that is smaller that has 51 and 88. There's no group that is larger than 95 because 95 is the largest value there. I have to go and keep recursively partitioning things until I'm down to groups of just one item. So in the case of my left partition here, where I had this pivot point 40, I'm down to 30 and 46. There's one item here. I don't need to partition this anymore. But I had to do another partition here of this group where the pivot was 95 because I had two items that were smaller. I picked 88 as the pivot point, so then I've got one item that's smaller, 51, and then I've got my pivot point of 88. Once I've gotten down to this level here, I'm basically at my base case. I can go and start returning things. And as I go and return, I'm reassembling things in sorted order. I just have to take the stuff that's in the left partition, and then the pivot, and then the stuff that's in the right partition. So you can see here that I just took 51 and 88, and those come back up, sorted. I'll go through and combine the 51 and the 88 and 95, and those come back up sorted. Then I'll combine from my left side 30, 40, and 46. In that order, those are sorted. And then I just work my way from left to right to go and sort the final thing. So I'll have everything from the left partition, then my pivot, then everything from the right partition. And it all comes back sorted. Let's go ahead into Eclipse and see how we can code this up. Here in Eclipse, I've opened up the Quicksort class that was part of the starter code for this lecture. In addition to our recursive method, we're going to have two helper methods for our implementation here. Let's go ahead and code up the first one, which is actually really simple. This one's just going to go and swap the values between two elements. This is something that we could just roll into our other code. We're going to do this task twice, so I just decided to go and spin it off as its own function. I'm going to make this be protected because it's not something we want externally visible like we might with a public method. It's going to be static, and we're going to have the t generic parameter with the same restrictions that it goes and extends comparable like we've been doing with all of our other implementations. This will be a void return type, and I'm going to call it swap elements. It's going to go and take the array that we're going to do the swap in, which is of type T. We're going to call it swap array, and then we'll have an int called index A and another one called index B. Inside the body for this, we're going to go and write code that will swap the values between indexes A and B. We're going to need a temp variable to go through and keep track as we go and make those swaps. So I'm going to say var temp equals swap array sub index A. Once I have index A's current value safely stored in temp, I can go and override it with the value from index B. So we'll say swap array sub index A equals swap array sub index B. And then I'm going to go and place what's in temp over in index B. So we'll do swap array sub index B equals temp. I'm going to give this method some Javadoc. So we're going to swap two elements in array for the description. T is the type of data being stored. Swap array is the array for performing our swap. Index A is the index of first element, and index B is the index of our second element. Our other helper method is going to go and partition the chunk of array that we're trying to sort into the parts that are less than and greater than our pivot value. Our method to do this will be protected since it's basically internal use here. We'll make it be static as well, and we'll have our t generic here that extends comparable question mark super t. This method is going to have an int return value because we're going to go and return the index of our partition pivot point here. I'm going to go and just call this array partition, and it's going to take three parameters. The first will be an array of type T. That'll be our sort array. We'll have an int for our left index of what we're trying to sort, and an int for our right index. The first thing that we want to do inside this method is go and figure out what value we're going to use for our pivot, and that's going to be the rightmost value. There's really not any particular reason to select a specific value. It's easy to just go and use the fixed position, so we're going to go through and work with the one that's in the rightmost spot here. So we're going to determine pivot value, and I'm going to create this var that I'm going to call pivot value, and I'm going to set equal to sort array sub right index. We're likely going to have to move some values around as we go and partition our chunk of the array into things that are less than and greater than our pivot. So what we're going to need is a variable to keep track of our current index where we're going to go and move stuff to. I'm going to go and call this swap index, and I'm going to set it to left index -1. We're going to start off basically at the left side of the area we're trying to sort here. We're doing the -1 part because we're going to go and increment this index before we go and actually swap anything. Once I've got that variable created, I'm going to go ahead and do a loop. And what we're going to go and do is we're going to move values that are smaller than the pivot value to the left. So they're going to end up actually, when we're all said and done here, to the left of where our pivot value itself is actually stored. I'm going to do a for loop for this, and I'm going to go and create current index, and I'm going to initialize it to our left index. So we're kind of starting off with the first element that we want to take a look at, and we're going to loop while current index is less than right index. I don't need to go and check right index because that's my pivot. So there's no point in comparing the pivot to itself. Each time through, I'm going to go and increment current index. Inside the for loop, we're going to have to look to see if our current item is smaller than our pivot. We'll do an if statement for this here, and I'm going to design this in a null-safe manner. So I'm going to use java.util.objects.compare rather than compare to. For my first argument, we're going to compare sort array sub current index, and we're going to compare that against our pivot value. And then for the comparator, we'll do nulls first with a natural order comparator for non-null values. So we'll do java.util.comparator.nulls first, and then inside the parentheses for that, we'll do java.util.comparator.natural order. And what we're going to look here is for the case where this returns a value that is less than 0, which means that the value that's in current index is smaller than what's in pivot value. And if that's the case, then we're going to actually go and swap stuff around. We'll increment our index for the smaller swap position. So we'll do swap index ++, and then we're going to go and swap values. And we'll use the swap elements method for that purpose. So we're going to swap within sort array. We want to go through and pass our index A as being swap index, and we're going to swap that with what's in current index. Once we follow out the for loop, we need to go through and put our pivot value in the correct location. And that's basically going to be 1 to the right of our swap index. So I'm going to create this int that I'll call pivot index. I'm going to set equal to swap index +1. And then we're going to go and move our pivot value, which in our case is our rightmost value, into the partition pivot index position. And I'm going to use the swap method for that. So we'll say quicksort.swap elements. I'm going to go and pass it sort array. We'll go and swap pivot index with the right index. And in terms of what we're going to go and return, we'll go and return pivot index from this method here. Let's go ahead and give some javadoc to this method. And again, note that I use the notation that these indexes are inclusive so that we don't have any question about if we can use the value or we need to do the value +1. Once we fought our for loop, because we've gone and looked at each of the elements, I need to go and determine where our pivot point is going to be moved to. And we're going to do that by just going and creating this var called pivot index. That is going to be our swap index plus 1. So it's going to go in the position after the last spot where we swap something to. We're going to actually go ahead and swap our pivot to that location then. And we'll call quick sorts class swap method here for swapping elements, and we're going to pass it sort array, pivot index, and right index. So that'll go and move the pivot value into the spot where it's in between things that are smaller than and greater than it, and we can just go ahead and return pivot index at that point. Let's go ahead and give this method some Javadoc. So we're going to go and calculate index of pivot point for use in partitioning array. T is the type of data being stored. Sort array is the data being sorted. Left index is the leftmost index to sort, and we'll say that that is inclusive. And right index is the rightmost index to sort, also inclusive. And we're going to go through and return the index to use for the pivot point. Let's go and work on the actual recursive method now. And I'm going to have this be protected because, as we've done with the other cases, we'll go and create a public method that's going to be a little bit easier for users to interact with. Be static here, and we're going to have our tGeneric with the caveat that it must go and extend comparable, and it's going to be a void return type, and I'm going to call this recursive quick sort. We'll take 3 parameters. First one is an array of type T that we'll call sort array. We'll have an int called left index and another int called right index. The first thing that we're going to do is we're going to go and check for our base case, and that's going to be where there's just one element being sorted, because at that point, if we just have one thing, there's not really anything to go and sort there. So if the left index is greater than or equal to our right index, we're just going to go and return. There's no point in continuing on here. We don't need to go and subdivide our data any further, which is what the recursive method does. Assuming that we do have more than one element, we want to go and partition it. So we're going to go and calculate where to partition the array by going and calling our partition method. So I'm going to create this int that I'll call partition index, and I'm going to set it equal to the result from calling quick sort and class with the partition method, passing it sort array, left index, and right index as arguments. Once I have the partition index, I'm going to go and place my recursive calls to go and subdivide things further. So we'll go and recursively sort left and right halves. So we'll do a call to the recursive quick sort method here to go and sort the left half. We're going to pass it sort array, left index, and partition index -1, because we want to sort everything up to and including the element before where our pivot is, which is the partition index. And then we'll also go and call recursive quick sort, passing it sort array partition index +1, because we're going to start sorting the element after our pivot, and we're going to sort up to and including right index. So these recursive calls will go through and take care of subdividing things here. And when we're all done, stuff will come back up the stack and we'll have a nice sorted result. Let's go and give ourselves some Javadoc here. So this performs quick sort on an array. T is the type of data being sorted. Sort array is the data to be sorted. Left index is the leftmost index to sort inclusive. And right index is the rightmost index that we're going to sort. To round things out, we'll go and make a public method to go and kick off the recursive calls to recursive quick sort. So this one's going to be public access modifier. It'll be static, and we'll have our tGeneric. This one's going to be a void return type, and we're going to call it recursive quick sort, the same as the other one here. But it's only going to have one parameter, and that's our array of type T that we're going to call sort array. Inside the body here, we're going to go and call the recursive method. So I'm going to call quicksort.recursive For the first parameter, that's going to be our array, so we'll pass sort array. We're going to start sorting at index 0, and we're going to sort up to sort array minus length minus 1 to go and account for the fact that we have the 0-based indexing. We'll go and copy our Java doc from the protected version of this, paste it up here on the public, and we'll just get rid of the 2 params for our left and right indexes, and we've now implemented quicksort. Let's go ahead and place a call to quicksort in our main method to go and sort the data that we're generating. So we're going to call quicksort.recursive and I'm going to pass it numbers. And then let's run this and we'll see our results. So we have our values here before we go and sort, and then afterwards you can see things are nicely sorted in increasing order. Quicksort has pretty good time complexity for its performance here. Best case and average case are both n log n. In worst case, it's big O of n squared, but worst case is pretty rare. You normally don't see that for quicksort. So performance is sort of comparable to merge sort in a lot of cases. And there's some variations here on quicksort in terms of how you pivot things that can go and eke a little bit more performance out of things. I've shown you a simpler example because even as complex as this was still a little bit easier to understand. As things tend to work, quicksort is generally a preferred go-to solution for arrays, as long as you don't have really big arrays. Sometimes with large arrays, performance isn't as great, but for most arrays, it works out pretty well. A variation of quicksort that actually has dual pivots is used in Java's built-in implementation of the sort method that's part of the arrays class. One nice advantage of quicksort over merge sort is that while merge sort goes and requires those temp arrays to go and store our left and right halves as we go and stitch everything together, quicksort doesn't require that. Everything is done in the existing array. So it has fewer memory demands, which if you're sorting a ton of data, that can sometimes be an advantage. So as you've hopefully seen here, there's a lot of different ways that you can go and sort data. And some cases tend to be a little bit better than others for different applications, depending on what sort of input data you've got, what size it is. There can be advantages to a variety of different approaches. But there's options available, and be aware of what's out there so you can go and find the best one for your own use case. For this lecture's participation project, I want you to download the participation project starter code from eCampus. Inside there, modify the merge sort class so that the algorithm will run in big O of n time if the data that we're trying to sort is already sorted. That's where we're going to end things for our look at sorting algorithms. If you have any questions, please join the Q&A session or send me an email. Thanks, and have a great day.